Jnanam Paramam Dheyam. Knowledge is supreme.
Hello students, welcome to the second module of this course, and in this module we will be focusing on process control. In the first module in the last 3 weeks we looked at different ways we represent process dynamics, and the whole objective of that exercise was to understand how processes behave. Now in this module, in the next few lectures, we will look at how do we use this information about the behavior of a process to manipulate the behavior so as to ensure that our system behaves the way we want. So that will be the focus of this module on process control. So for this first lecture, the objectives of this first lecture would be to develop block diagram representation for our systems, especially when we have a control system placed on top of a physical system, and then we will derive closed loop transfer functions, and lastly we will look at the different types of feedback controllers which we have. So earlier in the first week I had given you some glimpses about what is a feedback control. So feedback control is a way of controlling a process where we measure the controlled variable and use that information or use that feedback from the system to manipulate the manipulated variable. And we had seen that there are few advantages and disadvantages of having a feedback control. So in feedback control, the measured variable is the controlled variable, and because of that the advantage is it gives you direct monitoring. And this control strategy is also very robust. You don't need to know all the disturbances which are affecting the process, and because of that feedback control is one of the most commonly used control system, especially at a regulatory level, and that is why in this module on process control we will be heavily focusing on the feedback control part. In addition to that, there are some cons as well, like it is reactive, that it will take action only when the disturbance has affected the system, and we will see how that effect can be minimized by effectively designing this feedback control strategy. Now when I said feedback control is one of the most commonly used control strategy in industry, the actual correct way of saying that statement would be it is one of the most commonly used control strategy by man as well as nature. There are lots of examples in nature which follow feedback strategy. For the next few minutes I will give you some examples where feedback control has been implemented by nature or man in the domain outside of our chemical engineering. The human body is a very good example where there are lots of feedback controls loops which are present. So if I take an example, so let us take temperature control. Now human body maintains roughly 100 Fahrenheit or 98.3 Fahrenheit or 37 degrees Celsius temperature, irrespective of whatever are the external factors which are affecting human body. The outside temperature is very cold, and because of that the human body temperature tends to go down. So in that case, so let us say the temperature or ambient temperature falls. Because of that the body temperature tends to fall. In that case the body's internal mechanism is such that we will shiver, and when we shiver there is vibration inside the body, And as you know, vibrations cause increase in energy or increase in temperature, and because of this shivering, or let us say vibrations, that effect will be the body temperature will increase. So you can see that a decrease in the body temperature has caused or triggered a feedback action in terms of shivering, which helps us to increase the body temperature. Same thing is true when the opposite case happens. Let us say you exercise or run quite a bit, then your body temperature increases. In that case, what do? You sweat. Because of sweating, there is a phase change, and it is going to take the internal energy inside the body to cause that liquid to go out of your body, and because of that the internal energy of the body decreases, and this results in the reduction in body temperature. So again you can see that an increase in body temperature caused some feedback action inside the body, which resulted in reduction in the temperature. So human body temperature regulation is an excellent example of feedback control. The other case again very common is blood glucose level control. So whenever we eat carbohydrates, they get converted into glucose, and then the blood glucose level goes up. So whenever blood glucose level goes up, our pancreas would secrete an hormone known as insulin. So the secretion of insulin increases, and that helps you bring this digest this glucose, and then because of that the blood glucose level goes down. Now whenever you do fasting, that time the blood glucose level drops. Because of that the insulin level will also, the secretion of insulin will drop, and it will help you increase the blood glucose level to the desired value. So the blood glucose control inside our body is also an example of feedback control, and the controller here is our human body or pancreas. Whenever this controller is not functioning properly, you get diabetes. Which means your blood glucose level cannot be maintained with the desired level because of different sorts of problems which can happen, which essentially the idea is the insulin rate, the rate at which insulin is produced in the body is not adequate to control the blood glucose level to its desired value. Now, other commonly used example of feedback control by man is while we are driving. So whenever we are driving, one of the case, let us say we are driving a bicycle, then balancing is also an example of feedback control. So what do? Let us say we are driving a bicycle, it is going steadily, it is balanced, then no action is taken. As soon as let us say you go over a pebble and then you get inclined towards one of the direction, what is the natural tendency? That you shift all your weight to the other side, so that the center of gravity again shifts back to the center, and then you are able to maintain the balance. So when you are trying to balance, again it is a feedback control where you try to maintain a position of center of gravity. The other thing where you use feedback control is in terms of speed control. So if you are going uphill, then you have to provide more energy into your car in order to maintain the same amount of speed. So let us say you are going at the same accelerator pedal, and you hit uphill road. So let us say your car is going like this, and you are putting the same amount of acceleration. So you depress the accelerator to the same amount, and then the speed gets maintained because the road is flat. Now let us say when you hit an uphill part, now the same amount of acceleration is not going to give you the same speed. So in order to maintain the speed, what do? You press the accelerator more. So because of that, your car is able to maintain the speed on the uphill part as well. And then let us say you are going downhill. In that case, you will have to release the accelerator because the gravity will naturally provide you some additional force, and so the amount of force which you have to provide to your car reduces, and so by changing this accelerator pedal you try to maintain the speed within your desired value. So again, speed control when you do, that is also part of a feedback control. And lastly, direction control. Whenever trying to control the direction, there is a steering wheel, and if your car is trying to move towards one direction, then you will obviously move the steering wheel to the opposite direction, so as to make sure that your car tries to go into the straight line. This can be explained more, this can be visualized to a greater extent when you are trying to give direction to a canoe. So whenever you are pedaling a canoe, in that time, if your pedals are not synchronized, it will try to go into a zigzag form, and because of that you will always try to maintain it to go in the straight line path, and the direction of the current may move your canoe into one or the other direction, and you always try to counter that by paddling on the correct side. So direction control again is based on the feedback. Depending on whether you are swerving away from your direction, you will take some control action. So all these examples are of feedback control which are in general used. So as my point was, feedback control is a very commonly used strategy to control any process, and the same applies to our chemical engineering processes as well. So it is one of the very commonly used control strategy. So let us again try to revisit how whenever we want to implement feedback control on any system, how do we go about, and we will take an example of our surge tank. This is our surge tank where some flow comes in, which is our typically a disturbance, which is considered as a disturbance, and you try to manipulate this outlet wall so as to maintain the level inside this tank. So when we talk about the feedback control system, the first step of that is to measure the control variable. So the first thing will be to measure the level, we will call it as level indicator. So it will just take the current value of the level and convert it into some sort of electrical signal which will be able to drive the controller. So the next thing is that current value of the level gets compared with the desired value, we will call it as L set, and then we take the error of that signal, because we are interested in what is the difference between the desired value and the current value. So that difference is then fed to the controller. So let us call it as level controller. So it is going to act on this error, and then accordingly it is going to generate some sort of a signal, electrical signal, which will correspond to how much this valve should be opened, and then that signal will go to the valve, and accordingly it will take an action depending on the whatever is the controller signal, whether to open the valve or close the valve, and then the F out will change. When F out changes, that will have some effect on the height, and again this whole process will get repeated. So in terms of a feedback control system, along with the process you have these additional blocks. So this is your process, on top of that you have a sensor, you have a controller, and you have the valve, which is known as the actuator. So the feedback control system has these three additional components on top of this process, and in general if you see how this entire process is going to interact, what we can draw a boundary that the way we are going to interact with this system is that some disturbance may occur into the system, and then the control system should be able to reject that disturbance. The other way we are going to interact with this system is through this desired value. So, if there is some change in the process and we want to operate this tank at a different level, even though there is no disturbance, we will change the set point, and the control system's objective is to move the system from this current height to the new height of new L set. So, these will be the two types of ways we will be interacting with this feedback control system. Whenever we look at the objective of disturbance rejection, we had called it as regulatory control. Whenever the set point changes or operating point changes, that type of control problem we call it as a servo problem. So, we will look at how does the feedback control system behave when it is a regulatory problem or whether it is a servo problem. So, in the next step we will try to represent a process into its block diagram, and then we will look at how do we formulate the transfer function for this combined feedback control system when we are talking about a regulatory problem or a servo problem. So, let us start with the block diagram representation of this system. Even though we will take this liquid surge tank as an example, this block diagram can be drawn for any processes, and we will try to draw the general form of a block diagram. So, if we look at this original process of liquid surge tank, we know that there are two inputs into this process. One is F in and the other input is F out. Both of these are going to affect the output of this process, which is the height. So, we have two transfer functions. One is a transfer function from F in to the output. Let us say in this case is height, and the other transfer function is between F out and Y, and the actual output will be the addition of these two, the effect of F in and effect of F out. So, in general the way I can write this block diagram is there is some transfer function for disturbance. So, if there is a disturbance, it will have some effect on the output, and there is a manipulated variable, let us call that particular transfer function as Gp, and the manipulated variable is M. So, any system which has one disturbance input and one manipulated input will have two transfer functions, one for transfer function between output and disturbance and other between manipulated input and output, and then the net output will be the sum of these two things. And again by default we are actually considering the deviation variables in each of these cases, and this is the case when there is no controller which is placed, and we also call this arrangement as open loop process, or the response in the absence of controller we will be terming it as open loop response. So, this is the basic process which has a disturbance and a manipulated input. Now, we will try to expand this diagram and try to derive a block diagram for a feedback control system. So, our basic process remains the same. So, you have a transfer function Gd between disturbance and output, and we have one more transfer function Gp between the manipulated variable and the output. Now, on top of that we will have the control system. So, let us draw. So, the first thing of the feedback control system is that we want to measure the value of the controlled variable. So, we will have a measurement block, and the corresponding transfer function is say Gm. What we get is the measurement value, which ideally you want to be representative of the actual control variable value, and this measurement then gets compared, this will get compared with the desired value. So, let us say this is y set. So, we will compare it with the desired value, and then the difference of that is called as the error signal, and that error signal goes to the controller. So, the second block was the controller. It will take some action and it will give you whatever is the output of the controller, will represent it as u, and then that output drives the actuator, which was the control valve, which is GV, and the output of GV will be the manipulated variable. So, this way the feedback control system will have these additional elements which we had just considered, and then this final form has a closed loop. So, you can see that if you trace down in this direction, the information flows this way and then gets circulated back. So, there is a closed loop here, and whenever we have a feedback control or any control in general, we call it as a closed loop system. So, whenever the controller is on or whenever a control loop is placed, we will call it as a closed loop system, and you can see that that loop has this particular direction. And in terms of our earlier representation, you can again see that this block diagram represents the installation of feedback system, so that you can have some changes in the disturbance. Whenever we are trying to reject the disturbance, the controller will take an action, and then you may have some way where you objective when you want to change the desired value, a set point value, and accordingly you want the output to change in response to that. So, you can have a servo problem when these two variables are in play, or you may have a regulatory control when these two variables are in play. So, now we will try to derive the transfer function for this particular closed loop system. So, for that let us start with the output block. So, we can write that this Ys is the sum of two parts. One is the contribution from the disturbance and other is the contribution from the manipulated part. So, it will be equal to Gd times the Laplace of disturbance plus Gp times the manipulated variable. So, this is same as the open loop when there is no controller. And now, when we start about the feedback control, we will start representing or adding additional things into this module. So, we can write that this Ms is the output of the actuator. So, we will be representing Ms as Gv times Us, and then this Us is the output of the controller. So, Us is equal to Gc times epsilon s. So, by substituting these two, what we are going to get is Ys is Gd times ds plus Gc Gv Gp times epsilon s. Now, epsilon is the difference between the set value and the measured value. So, epsilon s is equal to y set s minus yms. So, let us now substitute that, and what we get is Ys is Gd ds plus Gc Gv Gp y set s minus ym s, and then lastly we can say ym is the output of the measurement or sensor. So, it is equal to Gm times Ys. So, we get Ys as GDDS plus GC GV GP Y set S minus GM GC GV GP times Ys. So, what we have is there are two terms in Ys. This is the disturbance term and this is the set point term. So, if we move this Ys term on the other side, then what we can write is Ys is equal to Gd over 1 plus Gp Gc Gv Gm times ds plus Gc Gv Gm over 1 plus Gp Gc Gv Gm times Y set S. So, this equation tells us that how the output is going to change in the presence of this feedback controller when a disturbance is affecting the process or a set point change is made. So, this is the transfer function which will represent the effect of disturbance. We will call it as a regulatory transfer function or GR, and this is the transfer function which will tell us the effect between the set point change and the output. So, it represents the servo problem. So, we will represent it as GS. So, these are the transfer functions for the feedback controller whenever we are working it as a regulatory controller or a servo controller. In reality, both these actions will be happening together, and then whatever is the output will be the effect of changes in disturbance as well as the changes in the set point. So, we will take a short break here, and when we come back we will look at different types of simple feedback controllers. Thank you.